So yeah, we keep changing the name to these. We're searching for, as we search for the definition of what they are, trying to come up with the names that'll stick to kind of explain what they are. So I'm going to be talking about the mystery of, first of all, what these galaxies are, as Gene kindly introduced, but also the mystery of where they came from. And try to treat this a little bit as a detective story. And it's really fun being on the ground floor of a new class of galaxies that's discovered, just finding out what they are and then trying to solve a mystery about where they came from. And a lot of people involved with this, in particular Peter van Dam and Bob Abraham, who led the way in this entire subfield that's rapidly growing. So here's a orientation plot, one way to look at the universe of galaxies. This is absolute magnitude or luminosity up here versus effective radius of galaxies. And here, for simplicity, just plotting quenched galaxies, Quiescent, from the dwarf spheroidals to the dwarf ellipticals up to the giant ellipticals, and cutting off there because we're not really going to get into the most luminous ones too much. So another way you could look at things is in terms of surface brightness. So these are lines of constant surface brightness from average brightness of 20 magnitudes per arc second down to 30 in the V band. And there's a lot of work, as we've heard about, looking for low luminosity dwarf spheroidals, ultrafaints, in terms of probing dark matter theories. And that's down in this region here. And it's well known that there's selection effects. It's very difficult to find these kind of objects. A lot of work discovering things down here. But less attention has been paid to these regions up here. It's been, I think if people thought about it, assumed that we know what's going on with these more luminous galaxies. It's down here that the mysteries are. But if you notice here, there's the sequence of galaxies, and there's maybe a couple up here poking up. And keeping in mind this is a log scale, that's a fairly large difference, and they're fairly low surface brightness galaxies. Those two there, those are from a LSB survey by Konstantin and collaborators about 20 years ago. And there was a whole series of papers back in that era of looking for low surface brightness galaxies. And they're very hard to study then and now. But I think it's been a little bit forgotten that this class of galaxies exists, and forgotten that perhaps we don't actually know what's out there. That as you push down to these low surface brightness levels here, I'm going to show as we're going to start filling in this area here, but we still don't know what could be up there in these even lower surface brightnesses. So this little subfield started with the Dragonfly array, which is this project by Bob Abraham and Peter van Dam, using the commercial grade cameras with some really nice technology to allow for low surface brightness imaging. It's not about having the biggest telescope, but it's about having the least contamination from various effects in your images. And one of the things that they were looking for things like the intracluster light and dwarf spheroidals and things, and they pointed at the coma cluster, and one of the first things that popped up was that they noticed a lot of fairly luminous low surface brightness galaxies marked here around the core. And they have low resolution images. They checked some deeper images with the CFHT and found that they were not just background or not just junk. And here's one that happened to be an HST image. So you can see that's this fairly red, featureless, spheroidal-looking galaxy. Very large. As Gene said, that we've gone after one of those so far and obtained a redshift confirmation that these are associated with the coma cluster. A deeper image with Keck just to see that it's not something being disrupted as far as we can tell. And now here's a plot of all those low surface brightness galaxies from the Dragonfly array, again on this plot. So extending this tendril, this sort of additional track of low surface brightness galaxies extending here. Off of the normal, say, dwarf spheroidals, dwarf ellipticals track. Here's another way of looking at it in terms of surface brightness and effective radius. Now this is a linear scale kind of to heighten the contrast with, these are normal disk galaxies, but higher surface brightness, and these are low surface brightness galaxies. They're not disks per se, but similar scalings to the Milky Way disk, but much fainter objects in total luminosity and surface brightness. So here's some basic parameters. This is a new parameter space being covered by these quiescent galaxies, low surface brightness, large size, luminosities and stellar masses about 10 to the 8th solar, effective radii 2 to 4 kiloparsecs, Sirsic index of about 1, so disk-like Sirsic index, 25th magnitudes per square arc second, surface brightness. So their luminosity is like dwarf galaxies, but size is like giant galaxies. So what do we call them? Are they dwarf or are they giant galaxies? All right, and Jean showed this picture already. A nice thing to point out here, I don't have it on here, but these two galaxies have the same luminosity. Okay, and a UCD that I sometimes have it on here. You could put a UCD on here, which is even more compact, and it's the same luminosity. Actually, this compact elliptical it's a little more luminous, but yeah, a factor of 10 more luminous. But it's interesting that you've got the same luminosity can come in two totally different size scales, and whatever theory you have for this needs to simultaneously explain this at the same time. So you say, well, what's the big deal? We've known about low surface brightness galaxies for decades. Well, these are a different beast. Here's a famous Malin 1. And low surface brightness galaxies, the ones that you typically will hear about, are fairly gas-rich, star-forming at some level. A lot of these ones, like Malin 1, have a fairly bright bulge in the center and these really large extended disks. These things look very different. They're redder. They're more spheroidal looking. They're not like the classical LSBs, although some of them popped up as a few outliers in the old samples of LSBs. We don't know except for one, which I'll tell you about. Well, I guess I'll tell you that basically the one that we've measured has no rotation, V over sigma of 0.1. Okay, so UDGs are a subset of LSBs, but that's a very broad class of galaxies. Here's a way to look at the colors. You can see by eye, hopefully, that those are fairly red objects. Here's a different way of putting on the red sequence blue cloud. So here's the red sequence B minus R color coming in here, and the UGG and the blue cloud down here, and the UDGs sit on the red sequence. That's in the coma cluster. This is another sample in the field, and it's a little harder to see, but there's the red sequence coming down there, and it apparently continues down to the UDGs. I think they're bluer because they're dwarf luminosity. Like they wouldn't have to be that blue. It depends on the metallicity. Anyway, this is all stuff that it's fairly brand new. We're still trying to understand things like the ages and metallicities, but just looking at the color sequence, they seem to fit in with the standard red sequence. So a basic fact, as far as we can tell about UDGs, they follow the red sequence. They seem to be quiescent, although we don't know the exact ages. They could be 2 gigayears old. They could be 13 gigayears old. Okay, so after the Dragonfly array, the Japanese group checked their Subaru images. They've been studying the coma cluster for years, and they found that, yep, they were all sitting there in their images. In fact, there were not just the 47 that the Dragonfly found, but they found roughly 1,000 of them in the images with much deeper imaging, higher quality. Here's a number density profile of how these things extend out in the coma cluster. This is about 3 megaparsecs here. They roughly follow the density profile of all the other galaxies modulo a core, and here it flattens off. And then once people knew to look for these things, they're popping up all over the place. A group has been doing deep imaging of the Virgo cluster for years, and once they knew what to look for, they found these things pop up in their images, UDGs. One of them in the process is disrupting. And in the past year and a half, there's been tons of papers coming out on observations about these things. It's been really rapid back and forth, about 10 letters, APJ monthly notices going back and forth in rapid succession. It's a fast developing field. So let me get a little more into some statistics. This is the number of UDGs in clusters. This is a nice work by a Canadian group looking at CFHT images and of 7 galaxy clusters of different masses. So you can see how many of these are there per unit mass of a cluster. So a Virgo mass has, of order 10, and you get up to a coma mass, you get into the hundreds. So it's a significant but a minor fraction of the galaxies in a cluster. And here's the density profile, as I showed again, now showing more of the core profile. It's the inside of about 300 kiloparsecs they turn over in a core, which is, if they're getting tidally disrupted, as you might expect for low surface brightness objects, that's kind of what you might expect. So, now getting into formation theory. This is a little piece that came out in the Scientific American about this thing, saying that the mystery of phantom galaxies may soon be solved. So we'll see if it's been solved or not. I'm going to start off with kind of the first most obvious formation scenario, which is, okay, there's lots of these things in galaxy clusters, and galaxy clusters have a thick ISM, And if lots of ram pressure stripping we can see in action, well, all these things could just be low surface brightness galaxies, gas-rich, fell in, they got ram pressure stripped, end of story. Okay, we didn't notice them before, but now we understand them, let's move on. Yosin and Becky did some hydro simulations of this process of dropping something in at redshift of 2 into a coma cluster-like type object and just following orbits and following ram pressure stripping process. You pull out the, this is a low, starts off as a low surface brightness gas-rich disk, and it's left off with as a quiescent low surface brightness galaxy. Amorisco and Loeb did something, they didn't do direct simulations, but just a similar idea that the UDGs are basically low surface brightness galaxies with a relatively high spin, which means they have larger disks, and the number statistics, the number of objects, fits in with what you expect from high spin halos in lambda CDM. Kind of part of the same story, I think. A couple of more quirks in this is that Oleg Needon had some, you could call it predictions of this back 2003, was studying galaxy transformations in clusters. And one thing is he dropped an LSB into his model and found that not just by ram pressure stripping, but by tidal heating, that you could heat this up into a spheroidal galaxy. You truncate the LSB disk and get a spheroidal, likely outcome being a gas-devoid spheroidal galaxy. And I think he himself even forgot about that prediction, but it could be relevant here. Andy Burkert's been doing some new work of, again, modeling ram pressure stripping, but looking at what happens if you have a lot of gas, very high gas fraction, and instantaneously remove it, then that loss of the binding energy allows your galaxy to expand, and you could go from a normal disk to a puffed up disk. Now, the trick is here that you go from a normal thin disk to something that's like a puffy disk. So this is kind of a generic potential issue with this all these scenarios of ram pressure stripping, is that they're fundamentally disk galaxies that got stripped, except possibly Oleg's might be more spheroidal. So what you expect to get are maybe disky-looking objects. So the question is, what do the observations show? And of course, you never know in 3D what any individual galaxy looks like, or something like this, you don't know what it looks like. But if you get enough of them, you get 1,000 of them, you can start doing statistics, and they mostly look like this. They look round. And if you look at the histogram of axis ratios, it's this red distribution. It peaks at an ellipticity of 0.25, which is very different from a projected disk ellipticity. So they don't look like disks. They're more like elliptical galaxy type ellipticities, fairly round. This is a different, there's been a bunch of papers, they all find the same thing. Again, axis ratio versus distance from the cluster, going pretty far out. And again, it's the same type of axis ratio. They look like spheroidal galaxies. And so on average, the UDGs are spheroids, not LSB disks. So if you want to start off with some low surface brightness disk, you have to find a way to really puff it up after you puff it up in both directions, not just in radial direction, but also in the Z direction. Another clue here to the mystery is that these things are not just found in clusters, but they're found all over the universe wherever anyone looks. This is the second spectroscopically confirmed UDG that was part of a collaboration here. It was toward Andromeda. We actually thought that it was a satellite of Andromeda, a new one of those AND 30 something or other galaxy, until the Russians went out and banged away with their 6-meter telescope and got a spectrum and found out that it was whatever that is, 70 megaparsecs away. So it turned out to be a UDG. And it's in the field, very large, 5 kiloparsecs. Although it is kind of on the outskirts of a cluster, so there is a possibility that this is not a real field UDG, but it's the backsplash galaxy. A lot of you know what that's about. But after that, there's been other work come out from Roman and Trujillo finding these all over the place throughout the cosmic web in group lower density environments, going out into the filaments from clusters. So they seem to be everywhere. And as I showed at the first slide, Julian Dalcounten found these in the field back 20 years ago. So whatever formation scenario you have, or there could be multiple formation scenarios, you need something that explains them in the field. So just to summarize the observations again, or some of the observations, again, there's these large sizes, low surface brightness, but keep in mind these things look undisturbed, low Sirsic indices, spheroidal, red sequence, all environments. These are all pretty key properties for UDGs. So what we want is some formation mechanism that does not involve galaxy clusters necessarily, predates the clusters, and is perhaps some kind of novel quenching mechanism for the dwarfs. So enter the archive on Friday. a new paper appeared from work that Avishai is involved with. This is Decentio et al. And this is, I don't know if somebody else mentioned this set of simulations already. This is the Nihau simulations. And some really strong internal feedback. It turns out they looked at these very bursty feedback with strong stellar winds produced these very extended galaxies, not only expanding the dark matter, but also the stars. So a lot of the properties look a lot like the observations. Dwarfs with large surface brightness large scale lengths, low surgical indices, they at least temporarily look quenched. But it's not clear yet. I'd like to hear more about it. You see how disturbed that looks. I don't know what happens if you add noise. I don't know if these have the same kind of low level of disturbance you see in the observations. Also, this is a face-on projection. Again, we don't know if these are basically disks or not, or they're spheroids. And we'd also like to know about the masses. Again, something that Gene introduced. So the first hint that these things might have unusually high masses is just the fact that they survived as close to the coma cluster core as they do, and you can do some simple tidal disturbance analysis here to give you some level of the dark matter content. Within 5 kiloparsecs, a dark matter fraction of 98%. So they could be extremely dark matter dominated. We call them failed galaxies. I mean, there's some people talk about, oh, are these dwarfs? Are they failed Milky Ways? I'd like to kind of get away from that a bit and say, just failed galaxies in general. They don't have to be Milky Way masses, but just interesting if they're very high halo masses for their luminosities. So we need to measure masses, interglobular clusters. Okay, there's two ways we're going to use globular clusters, and what's nice is that we've found globular clusters around some of these galaxies, and you can do this in two ways. One is you can use them as dynamical tracers, as Gene talked about for the giant galaxies. You can use them for the fainter ones as well. And the other is you could just count up the number of globulars. And that comes from a scaling relation I'll show in a minute. But basically, people have been collecting for decades counts of number of globular clusters versus luminosity or stellar mass, and you get this somewhat bent correlation here. There's the Milky Way, so a few times 10 to the 10 stellar masses and 160 globular clusters. As you get down to dwarfs, you get 10 or below, or you start getting no globulars at all. Well, these things are outliers from that relation. So whatever weird effect caused these things also did something weird to their globular clusters. And keep that in mind, I think there's going to be some controversy for a little while at least about the masses, but whatever happens with that, this is still an observation we need to understand why the globular clusters are overabundant. So, okay, what you can do with those globular clusters is it turns out that if you use a standard stellar halo mass relation and you map it onto this curve, you get a fairly flat ratio between the number of globulars and the halo mass. So you can convert that globular cluster number into a halo mass. Say that high specific frequency means an overmassive halo. And which is one way to interpret that. I'll show the numbers in a minute. Another way is to go ahead and do the kinematics and dynamics. So we've done that using globulars for one object, and Peter van Dokkum went out and spent 4 nights with Keck banging away on another one to get the stellar velocity dispersion, sort of the holy grail of this, and got a pretty high velocity dispersion. And what you get, this is a mass to light ratio with a half-light radius. Using one of these mass estimators that we just heard might be a little bit suspect. But they both these objects seem to be dynamically outliers from a standard relation mass to light ratio. If you plot that, if you take all these numbers, put them together, globular cluster numbers, dynamics, etc., this is what you get for the halo mass to stellar mass, and they seem to be outliers. And this one being consistent with the halo mass of the Milky Way, even though it's 2 orders of magnitude fainter in stars. Now, there's some. I don't know if it'll come up. There's a bit of controversy now about how to interpret this with the paper that just came out on Friday and things, but it's a lot of interesting work in progress. I'll just skip over that and say, if these things are overmassive, or if all these kind of simulations are only giving disks and not spheroids, we need some third formation mechanism for UDGs. The only thing I've seen in the literature that might be relevant is something that Riccati, I think, talked about, or no, Katz talked about here a couple years ago. Early globular cluster starbursty star formation that might have quenched the galaxy and formed something that was basically a failed galaxy. Oh, so before I show my summary, just want to invite everybody. There's a deadline coming up for a conference next year. It might be of interest to a lot of people. And pretty fascinating place, the Galapagos Islands. It's about baryonic galaxy halos. It's a very cool, exotic place, but it's actually not that expensive. It's very cheap to get there from the US as far as these things go, and accommodation is fairly cheap. So don't be put off by being remote. it should be lots of fun, and deadline's coming up toward the end of the month, so I hope you'll all be interested in registering. Okay, so back to the science. The summary of ultra-diffuse galaxies is a novel class of low-luminosity galaxies, quiescent spheroidal galaxies found in all environments. They appear to be unusually rich in dark matter and globular clusters, so we can say, well, maybe some galaxies are not too big to fail. These might be some kind of very early quenching mechanism. They formed and died very early, and that's why we call them ghost galaxies. So thanks for your attention.
Okay, questions?
Hi, nice talk. I was wondering on the luminosity size plot, the sort of bimodality of it, is that real? Are there no observations in the middle area?
You know, I'd like to know that. Yeah, if somebody wants to write a paper on that, that's a good question to look at. I don't really know.
Same question. Excellent. Well, I had a quick question. So given that there may be 1,000 in the coma cluster, doesn't that already tell you they're probably not galaxies that were of order of the halo mass of the Milky Way? I mean, we only expect maybe 100 of those in the coma cluster just from dark matter kind of simulations.
Yeah, that's what I said. Yeah, exactly. Good question. That's why I said let's not get distracted by this question, are they failed Milky Ways? Like the failed Milky Ways would be just sort of the most luminous ones might be Milky Way mass, but most of them are less luminous objects. They wouldn't be Milky Way mass halos.
Well, I guess less massive also than, right? I mean, less massive in terms of dark matter than the Milky Way.
Right, so they'd be excess 10 to the 11 mass halos, so there could be a lot more of those.
Yeah.
So just in terms of numbers, what fraction of galaxies at luminosity of, say, 10 to the 8 would fall into this class?
Yeah, I haven't run those numbers yet. I think in the coma cluster, I think I've seen numbers of, say, 10% or something. Don't quote me on that, but it's sort of a pretty small fraction. It's not like it's going to change your halo counts or something like that, which is sort of similar question there. But it's significant. They're not like some super rare objects.
Okay, and one last question from Eric.
So it's kind of barking up the same tree of trying to understand a relationship with a possible field population. It looks as if the color distribution for the wider population, the Roman and Trujillo paper, was consistent with being actually pretty star-forming in terms of the color distribution. And so it was, and as you pointed out, folks have been finding low surface brightness galaxies for years. These are, I think, unusually low surface brightness, as would happen if you dumped it into a cluster. So I guess are you aware of a kind of attempt to quantitatively match the poorly known space density of low surface brightness galaxies of comparable luminosity and halo mass in the field to their possibly stripped counterparts in the cluster? I mean, there's some bookkeeping that I think might illuminate if it's a plausible or a ruled out formation path. Yeah,
that would be great to do. Just to mention, yeah, it is a little hard to tell with the colors what's going on, but the other thing they did look at was, again, the axis ratios in the field. Still, they don't look disky. Again, they're round. So.
Okay, thanks again to Aaron.
The Dragonfly Array, which is this project by Bob Aram and Peter von Dockum, using the commercial-grade cameras with some really nice technology to allow for low surface brightness imaging. It's not about having the biggest telescope, but it's about having the least contamination from various effects in your images. And one of the things that they were looking for things like the intercluster light and dwarf spheroidals and things, and they pointed at the coma cluster, and one of the first things that popped up was that they noticed a lot of fairly luminous low surface brightness galaxies marked here around the core. And they have low resolution images. They checked some deeper images with the CFHT and found that they were not just background or not just junk. And here's one trying to solve a mystery about where they came from. And a lot of people involved with this, particularly Peter von Dockum and Bob Abraham, who led the way in this entire subfield. It's rapidly growing. So here's a orientation plot, one way to look at the universe of galaxies. This is absolute magnitude or luminosity up here versus effective radius of galaxies. And here, for simplicity, just plotting quenched galaxies, Quiescent, from the dwarf spheroidals to the dwarf ellipticals up to the giant ellipticals, and cutting off there because we're not really going to get into the most luminous ones too much. So and another way you could look at things is in terms of surface brightness. So these are lines of So yeah, we keep changing the name to these. We're searching for, as we search for the definition of what they are, trying to come up with the names that'll stick to kind of explain what they are. So I'm going to be talking about the mystery of, first of all, what these galaxies are, as Gene kindly introduced, but also the mystery of where they came from. And try to treat this a little bit as a detective story. And it's really fun being on the ground floor of a new class of galaxies that's discovered, just finding out what they are, and then fairly low surface brightness galaxies. Those two there, those are from a LSB survey by Gillian and collaborators about 20 years ago. And there was a whole series of papers back in that era of looking for low surface brightness galaxies. And they're very hard to study then and now. But I think it's been a little bit forgotten that this class of galaxies exists, and forgotten that perhaps we don't actually know what's out there. That as you push down these low surface brightness levels here, I'm going to show as we're going to start filling in this area here, but we still don't know what could be up there in these even lower surface brightnesses. So this little subfield started with the constant surface brightness from average brightness of 20 magnitudes per arc second down to 30 in the V band. And there's a lot of work, as we've heard about, looking for low luminosity dwarf spheroidals, ultrafaints, in terms of probing dark matter theories. And that's down in this region here, and it's well known that there's selection effects. It's very difficult to find these kind of objects. A lot of work discovering things down here. But less attention has been paid to these regions up here. It's been, I think if people thought about it, assumed that we know what's going on with these more luminous galaxies. It's down here that the mysteries are. But if you notice here, there's the sequence of galaxies, and then there's maybe a couple up here poking up. And keeping in mind this is a log scale, that's a fairly large difference. And